Hi and welcome to our next session here in our chapter on regularization. Here I will now continue the deep dive into L2 and L1. So basically we'll proceed with a pretty similar analysis for the geometric analysis of L1 penalties as I've done for L2. So we'll take a look at how L1 actually transforms the unregularized minimizer to the regularized version, and then again we'll see the soft thresholding operator in action as a result of that. And I have to simplify things even further here to proceed with a, easily understandable analysis. So what's the formula for our regularized risk? Well, we have it here. It's the empirical risk plus the L1 penalty. Now we can compute the subgradient of that, which looks like that. And we can also now see that unlike in L2, the contribution to that gradient doesn't really scale in any form, especially not in a linear form with the parameters. It basically is influenced by the sign of the parameters. And again, we'll now do an quadratic Taylor approximation of the empirical risk, again around the minimizer theta hat. So theta hat is supposed to be the minimizer of this here. Now again, then we approximate the regularized risk by the approximation of our empirical risk, which is this here. Again, this is second order. And again, remember that the linear part vanishes because the gradient at the location of the minimizer theta hat must be 0 because we're at the stationary point, okay? So, and that's the approximation of our amp. This thing here is the approximation of our amp. And then we add in the regularizer, in this case here L1, to get an approximation of our reg. Now, even with that thing, it's not so easy to deal with, especially because of the non-differentiability here of this L1 term. So I'll cheat even further and simplify further by assuming that H is actually of diagonal form. I probably really can't do that. Well, I guess I can maybe again assume something like a Mahalanobis transformation, whatever. But in any case, for a linear model, this would basically mean that I'm assuming this orthonormal design, which we looked at before, so that this holds, just accept that as a simplification so we can get any form of intuition here in this analysis. So I'll now assume that H is of diagonal form. This means because we are at the minimizer and H is supposed to be positive semi-definite. That means that all of these entries here must be non-negative. The nice thing is now if we insert this diagonal structure here, so if H is diagonal, well, then this second part here simply looks like that, right? So it's simple to see. I'm not sure whether I have to explain that. Maybe I have to. So what happens here in this multiplication? Well, if there's a diagonal matrix in the middle, this basically means that this basically becomes a squared sum. So I guess we could write it like, let's say this is a diagonal matrix here, and then we have some, and this here is this difference vector, right? So then it looks like this, right? So what would happen if we would have the identity in the middle? Then it's basically something like this, right? So we sum over these squared elements of Z. But if there's a diagonal matrix in the middle, this D, then we multiply all of these elements with the terms on the diagonal, okay? And this is exactly what I'm doing here, right? So there are these differences, theta j times theta hat j. We square them, and then we multiply them by this thing on the middle. And I also have to incorporate the 1 divided by 2. In the factor here, this thing. Okay, so we now have established that we have this middle form here, that this middle form can be written like that, or this middle element can be written like that. But more important than this, I don't know, algebraic yada yada, is we take a good calm look at the resulting structure. And if you look at that, you can see now that we have this constant term here, which we do not really worry too much about anyway in optimization. But then for the remaining terms, these are basically separable sums where each element, where each component with respect to j only refers to theta j and nothing else. So this is actually a separable function. So you could also say that this function can be written like that. So it's j terms where we have these functions gj that only depend on theta j, right? This is the underlying structure. And this is super nice for optimization because that basically means we can minimize each of these individual guys here separately, which means effectively we are solving a couple of univariate problems that we can all minimize separately. And this is exactly what I then did. And there's also a deep dive on the web page that shows that this result here actually holds. And again, you can see this resulting form of the soft thresholding operator that now tells you how theta hat is transposed into the regularized version for the LeSU. Okay, so what does this actually say? It says we have to compare this here, right? So we have to compare the absolute value of theta hat. I'm not saying j in every instance, right? Because we're just looking at one element. So we have to compare the absolute value of theta hat with lambda divided by this entry of the Hessian matrix, okay? And if that's actually larger than 0, we take that, okay? And if it's negative, then we cap it to 0, okay? So I guess it's easier to visualize that and to understand it visually. And this is exactly why I did that on the next couple of slides. So again, here in the background, we have these contour lines. Yeah, this is our unregularized objective. Here, that's the location theta hat of our minimizer. And I will now consider the first axis. Now I don't have to do any weird and complicated rotations. It's me just assuming this diagonal structure of H. And these gray lines here, they are simply the canonical axes passing through the origin. The more interesting things are the yellow dotted lines here. So this is actually the limit from our soft thresholding thing. So this is this here, okay? This is lambda divided by the entry of the Hessian matrix. And if we are inside of that limit, and this is what happens here, again, see, we are now looking in a direction where the contour lines actually change somewhat slowly, so there's not so much curvature going on, so loss risk changes slowly. So this is a less interesting direction, right, for risk minimization, expressed by the fact that this entry on the Hessian is somewhat small. If that's small, with higher likelihood, we are inside of that limit, right? Inside of these bounds. So we can either be inside of these bounds with higher likelihood if the lambda is large, right? So if we regularize more, or if the H entry is actually small, because we divide by that, and that happens if the direction we are looking at is less interesting for optimization, if it doesn't reduce loss by a lot. And this is exactly what happens here. In this case, we are inside of the limits. So we now shrink to the 0 bounds through the soft thresholding operation. And then we do that also for the second direction. Here we have a different capital H value. It is now larger because loss along this direction here changes more quickly. So this is a more interesting direction for optimization. So because of this, we are now actually outside of these bounds, which means we do not shrink completely to the zero, but we just shrink by this amount here, okay? And then at the end, we put these two operations together. So this here and this here, and then we arrive at this point, which is our lasso regularizer, okay? So this again shows you that, we again produce sparsity. So it's kind of a further visualization of this soft thresholding operation, explained a little bit more in context of the curvature of our unregularized risk and in terms of which directions influence optimization more and less, or let's say risk minimization more or less. Okay, that concludes this section here. See you in the next one. Goodbye.